Okay, so for today class, okay, we may discuss on the soil dynamic, okay, and then right after this introduction part, okay, I will lecture on the shallow foundation, okay, on the view of the soil dynamics, okay, and after the shallow foundations lecture, then we may discuss on the machine foundations, okay, which is discuss on the use of the pile foundations. Okay, it's very interesting topic. Okay, however, with some limitations of the reference. Okay, which is I only refer to one textbook, which is DAS. Okay, so the discussion still rely on what we call as on the result from several what we call as a research result. Okay, so from the research output result, I guess it is still a straightforward calculation, okay, especially for the shallow foundations. Okay, so when it comes to the pile foundation, okay, so the discussion is more related to how the behavior of the structure, okay, where we need to make sure that the structure is not greater than the natural frequency of the structure, okay, should be greater than the frequency that's been provided by the seismic or from the vibrations. Okay, so there are no direct calculations, okay, to discuss on the bearing capacity, especially for the deep foundations. Okay. Okay, so on the soil dynamic, okay, the contents will be on the introduction, okay, soil structure interactions, wave propagations in soil, and then I will share with you, okay, some of the methods, okay, that could improve the ground by using several of stabilization or ground improvement methods, okay, especially to reduce the impact from the vibration or from the earthquake. Okay. So yeah, we need to agree that most of the structure or most of the construction activity, okay, will rest on the ground, okay, starting from the natural slope. Okay, so we need to check for the stability. Okay, and then when we want to develop for any area, okay, at the slope, so we need to do some cutting, okay, which is to allow development of a road, for example. And then there will be needs, okay, to have a dam, okay, especially to supply or to produce an electricity. Okay, so we need to build a dam. Okay, so either it is a concrete dam or what we call as a earthen dam. Okay, so it also rests on the soil. Okay, so then the constructions of the building, okay, where all the structure, all the loads from the structure will be transferred to the foundations. Okay. And they will be needed to have excavations, okay, where we use a supported methods, or commonly we call it as a brace cut, okay, so to allow for any construction of basement. Okay, then there will be needs to have a tunnel, okay, to what we call to overcome the system of the supported excavation. And when we want to design for a roads, okay, which is the level is high from the ground level, so we need to construct for the road embankment. Okay, and for example, the construction on the soft soil, which is nearby the sea side. Okay, so then we need to improve the area. And the last thing is the constructions of the offshore foundations, okay, offshore platform that we need to design for the offshore foundations. Okay, so at all civil engineering begin with the geotechnical engineering. Okay, so it's very important for us to know, okay, to have some clear picture, okay, on the importance of the geotechnical engineering. Okay, so these are a simple cycle, okay, for a construction. Okay, we have here a construction site, okay. Then to develop this area, okay, so we need to understand the characteristic of the site itself, especially on the soil or on the ground. Okay. So by having soil investigations, okay, then we can get the sample, okay, either in situ or we need to send to the laboratory, okay, for testing. Okay. So all the important properties or information from the soil, either from the lab or from the site, okay, so we may use it for the design process. Okay. So in the design of this, okay, all these properties will be used, okay, for the design and analysis. Okay. Then later on, we may come up with the design and then construct whatever structure, okay, on the ground, okay, at the construction site. Okay. So that is a typical geotechnical engineering project team. So for the main important in the design, okay, is to make sure that, okay, the structure is able to provide a good or comfort serviceability, okay, and also prevent for any failure, which is collapse. Okay, so in the design, okay, we discuss on the serviceability limit state (SLS), and then we also have the ultimate limit state (ULS). Okay, so normally when we design, we may use the design load. Okay, so the design load should be monitored. Okay, make sure that it not reach the allowable settlement. Okay, in order to have a very good to prevent for any settlement and also to prevent for any tilt. Okay, so this example for a Pisa tilt tower, okay, which is in Italy. We also have one in Malaysia, okay, the Teluk Intan Tower Clock. Okay, so I went there and then I got an opportunity to climb up to the top of the tower and then to clock what we got to twist yeah to twist the what we call the regulator, something that to twist the regulator, okay, to make sure that the clock can be work for 2 or 3 days for the next following days. Okay, so then this is example of the collapse failure. Okay, I'm not sure which area is it. Okay, so this is the a part for a structure and also for a geotechnical engineer, okay, to look on it. Okay, so traditional soil mechanics and geotechnical engineering design was predominantly concerned with soil strength, and stiffness, so that the design engineer could define the failure state of the soil and or control excessive deformations of the soil structure. Okay, so that is a common work, okay, for a designer, okay, to make sure that to identify what is the failure state and also to prevent for any excessive deformations of the structure. Okay. However, that is under a static, what we call a static loads. Okay. So in this circumstance, the loading is considered static and the strain imposed within the soil may vary from about 10 power by -3 in service to a few percent at failure. Okay. So there is a common strains allowed, okay, to prevent for the failure and also to make sure that it can provide a good in serviceability. Okay. So many circumstances where cyclic or dynamic loads are applied to the soil either by natural force such as earthquakes, wind and water wave, or from man-made sources such as bomb blasts, traffic loads, and machines foundations. Okay. So there will be a source of cyclic, okay, or vibration, okay, either from the natural force or from the man-made source. Okay. So the type of dynamic loading in soil or the foundations of the structure depends on the natural nature of the source producing it. Okay. So dynamic loads vary in their magnitudes, directions, or position with times. Okay. Periodic loads is a special types of load that varies in magnitudes with times and repeat itself at regular interval. Okay, so this is some of example, okay, where the author tried to describe, okay, what is the source of the load of this dynamic load. Okay, for example, based on the time. Okay, for example, operation of reciprocating or rotary machines. Okay. So non-periodic loads are those loads that do not show any periodicity. For example, wind loading on a building. Okay, this is caused from the natural wind force. So deterministic load are those loads that can specify as a definite function of time, irrespective of whether the time variation is regular or irregular. For example, the harmonic loads imposed by unbalanced rotating machinery. Okay, so this basically is a is a accurate force. Okay, that we can determine it. Okay, so non-deterministic load are those load that cannot be described as definite function of time because of their inherent uncertainty in their magnitudes and form of variation with time. For example, earthquake loads. Okay, so this is unpredicted. So it's very hard or very difficult to determine the exact time, okay, when will the earthquake load reach. Okay, so cyclic load are those load which exhibit a degree of regularity both in its magnitudes and frequency. Okay, while static load are those load that build up gradually over time or with negligible dynamic effects. Okay, so the common in our design, okay, we are more emphasized on the static load. Okay, however, okay, we also can include the effect of the cyclic loads in the design. Okay, most probably we are not include for any cyclic loads. Okay, because we are far from the ring of fire. Okay, which is the area which is Malaysia is far from the effect of the direct earthquake. Okay, however, we still can experience an earthquake effect. Okay, especially from the Indonesia regions. But now, okay, most of the design or most of the design should include the effect of the cyclic, especially on the design of a bridge. Okay, yeah, I've been to second Penang Bridge. Okay, so the design is could cater for the dynamic loads. Okay, so and then they install a rubber damper okay, within the pier and the bridge structure. Okay, so they mount the rubber damper, okay, to reduce the effect from the earthquake. Okay, so this an example, okay, of a dynamic load. Okay, so the low speed rotary machines, okay, it is a periodic loads. Okay, so we know when will be the loads uh, apply. Okay, and then it is constantly show a cycle, okay, on the load itself, okay, on the result, okay. Then we have what we call a single impact of a hammer, a vertical acceleration due to pile of the pile driving, okay. And then the last one is the accelerogram of earthquake. Okay, wait a minute. Okay.
So the
So
video being recorded?
yes.
All right, sir.
Thank you. Okay. So I will share the video in the e-learning later.
Betul, sir.
Okay. So the magnitude of these dynamic loads are generally much smaller than most static loads and generate strain within the soil as low as 10 power by -6. So as we can see, okay, in the diagrams, okay, we have two main diagram, okay, this one, and this is a group of diagram to explain on the shear strain. Okay. So for this diagram, okay, so it discuss on the time of loading. Okay. So the time is very short, okay, and also the number of the cycle. Okay. So we can have here three type of groups, okay, to discuss on the number of the cycle, okay, where it have a shock, okay, impulse can normally refer to the blasting or bombing activity, okay. So the cycle is, for example, um, um, the minimum the dynamic okay, the minimum of the cyclic loads, okay, is around 1 Hz, okay, 1 cycle per second, okay, while it can be more than that, okay. So depending on the loading event, so the number of the cycle can vary from single load. Okay, for example, for this blasting bombing, okay, but it happened in very short period of time, okay, compared to the static problems, okay. So it can for example, for a temporary permanent structure, which is a static load, okay, so it can be there for more than ages, okay. Okay, so then we have a wave vibrations, okay, or wave propagations generally applied to earthquake events and construction activities where a number of loading cycle occur or from 10 to 1,000, the frequency from 1 to 100 Hz. So the last is the number of cycles is inordinately large, okay, such as those associated with machine foundations here, and also from the traffic loading, cars and trains. Okay, so in this case, the sort behavior can consider as potentially fatigue related. Okay. So although the magnitude of these dynamic loads are often much smaller than static load, the initial force may become important and must be considered in geotechnical design. Okay. Okay. Over recent years, it has been shown that the deformation behavior of soil is heavily dependent on the level of shear strain. Okay, so this is the shear strain. Okay, while this is this is the shear strain. Okay, while this is the shear modulus. Okay, so in this figure, okay, both of this figure, okay, the shear strain dependent behavior of soil. Okay, so it means that we have a several type of structure. Okay, which is very sensitive. Okay, to any movement. Okay, for example, for retaining wall, foundations, tunnels. Okay, so it can be seen that for a very small strain, okay, such as those induced by wave propagation or vibration, the soil is elastic and recoverable. Okay, so that there is no permanent deformation. Okay, at this strain, both the number of the loading cycle and the rate of the loading have a negligible effect on the soil behavior. Okay, so at the intermediate strain ridge, okay, the soil is elastoplastic and irrecoverable. Permanent deformation occur, usually associated with a crack and diffraction settlement of structure supported on the soil. Okay. So at this strain, the number of the loading cycle and the rate of loading both have an effect. Okay. So in this situation, okay, so they come up with a typical, they consider as a small strain, okay, and this is the type of the structure that depends on the shear strains effect. Okay. So for example, a tunnel, retaining wall, a deep, okay. So at higher strain, the material is here, increase in shear stress. Okay, these are typically associated with soil failure, compactions, liquefaction, and non-clay soil. Okay, so for the large strain, okay, normally it just rely on the soil itself. Okay, so in that case, okay, some of the, we also have a special triaxial, okay, where it can carry out for a dynamic or cyclic load. Okay. So for example, for this banded element, okay, so we can monitor or we can get the value for the shear modulus. Okay. So that's why it's very important, okay, for us to gain the value for the shear modulus, okay, in order to cater for the small strain effect. Okay. So for example, for this case, okay, so it discuss on the shear modulus and the damping value G and D. Okay, for a common type of soil failure, okay, so we may rely on the frictions, angle, and cohesions. Okay, so that's why in some of the numerical software, okay, when we want to apply for the effect of the what we call as of the vibration. Okay, so we need to include the value for the shear modulus and damping. Okay. So this is an example of the initial moving to resist a change in speed or directions. Okay. So a simple analogy, okay, when we drive a car or when somebody drive a car, so we sit as a passenger. Okay. So if the driver stop uh, suddenly, okay, so we feel that we are moving forwards. Okay. Or when the driver uh, accelerate suddenly, we also feel that we are going backward. Okay, so the same goes to the structure. Okay, where in actual the structure is in a static. Okay, if there are some accelerations on the soil, okay, so there will be effect of the initial force. Okay, so this is rely on the Newton first law. Say the object do not accelerate spontaneously. Okay, this property of matter which cause object to resist acceleration has been named as inertia. Okay, Newton first law is often called the law of inertia. Okay. Okay, most of the civil engineering structure involve some type of structural element with direct contact with ground. Okay. So as I mentioned previously on the diagram, okay, so most of the structure is rested on a soil. Okay, when the external forces such as earthquake act on this system, either the structure displacement or the ground displacement are dependent of each other. Okay. Even though the foundation structure and the supporting soil are two different physical entities, they form a system, and in terms of the mechanics of behavior of such system, one component influences the behavior of each other, the end product being the result of this mutual action or interaction between the two. Okay, so this is an early discussions, okay, on the study on the soil structure interaction. Okay, they call as a SSI. Okay, at the early stage of the design, okay, which is before 1980 something, okay, so they did not consider, okay, the SSI effect on their designs. Okay, so I guess right after a Kobe event, Kobe earthquake event, okay, in Japan, okay, so they start to include, okay, this SSI in their design. Okay. So the process in which the response of the soil influence the motion of the structure, and the motion of structure influence the response of the soil is termed as soil structure interaction. Okay. Conventional structure design method neglect the SSI effect. And neglecting SSI is reasonable for light structure. Okay, so we can use this just a conventional design. Okay, especially when we design for a light structure and relatively on a stiff soil, okay, such as a low-rise building and simple rigid retaining wall. Okay. However, the effect of the SSI becomes prominent for heavy structure, okay, first, and resting on relatively soft soil or loose type of soil, okay, especially for the granular soil. For example, nuclear power plant, high-rise building, and elevated highway on soft soil. Okay. So from there, we can get an idea to overcome these problems. Okay. So another way is by improve the soft soil conditions. Okay. Or for the structure itself, maybe we can put a damper systems, okay, which is to allow the, the vibrations, okay, transmit to the building, okay, and been reduced or minimized by the damper system. Okay. So damage sustained in the recent earthquake, such as the 1995 Kobe earthquake, they have also highlighted that the seismic behavior of a structure is highly influenced not only by the response of the superstructure, but also by the response of the foundations and the ground as well. Okay, so that's why I mentioned on the Kobe earthquake. Okay, it's very recent. The idea of the SSI. Okay? So when I refer to this DAS reference book, so they start to embark on this SSI. Okay, in 2005. Okay, in the modern seismic design code, such as the standard specification for concrete structure, seismic performance verification. This is Japanese JSCE 2005, stipulate that the response analysis should be conducted by taking into consideration a whole structure system, including superstructure, foundations, and ground as well. Okay. So the process in which the response of the soil influence the motion of the structure and the motion of the structure influence the response of the soil is termed as a soil structure interaction, SSI. Stiffness related increment of stress, increments of strain. Okay, a knowledge of soil stiffness is required to calculate ground movement and to obtain solution to problems of soil structure interaction, such as a load on retaining wall. Okay. So there is some introduction on the soil structure interaction, how they introduce this SSI, okay, after the 1995 Kobe earthquake event. So this is some example. When earthquake occur, the building and the ground vibrate with influencing each other. So the phenomenon is called dynamic soil structure interaction and is recognized as being very important for seismic design of structure. Okay. So this is the earthquake wave, okay, from the epicenter and transfer to the soil, okay, migrate in the soil, and then transfer to the foundations, either pile, basement foundations, or pile foundations, shallow foundations, okay, or basement foundations, and then transmit to the building. Okay. So the role of foundation. Okay. So under normal condition or under a static condition, it support the dead weight and the life load of the building, and also transmit this load to the ground. Okay. So this is an example of the function of the footing of foundations. Okay, we have a slab. The slab will be transferred to the beam, the transfer to the column, transfer to the stump of, yeah, pile cap if you are using the pile cap, using the pile, and then transfer to the foundation and transfer to the soil. Okay. So during an earthquake, transmitting the ground motion to the building, okay, bearing the building vibration and transmitting them to the ground. Okay. So when the earthquake event, okay, the wave will be transmit to the building, to the foundation, and then to the building, and then the wave also will be moving back to the ground. Okay. The ground and the building influence each other through the foundation, and this is called the dynamic soil structure interaction. So the degree of the soil structure interactions on response of building depends on the stiffness of the ground, okay, dynamic characteristic of the building itself, that is natural period or damping factor, okay, and foundation types. Okay, so we have here three dependents. Okay, stiffness, which is from the ground itself, and the characteristic of the building, okay, the natural frequency, okay, and also the damping factor. And the last one is the foundation type. Okay, so this is a typical type of a foundation. Okay, we have a spread foundation or shallow foundation. So we have a pile foundation without basement, and the C is the basement without pile, and the last one is basement with pile. Okay. So the position where the SSI take place through the bottom surface of the foundation, okay, which is the A1, the split foundation or shallow foundation, through the pile foundation, the B, through the bottom surface and the sideboard of surface, the C, and the D through the basement surface and the pile. So the influence of the SSI becomes remarkable and more complicated as the amount of contact between the ground and the foundation increase sequentially in order from A to D. Okay, so means that D is more complicated. Okay, in order to understand the soil structure interaction. Okay. Okay, interaction between ground and building during the earthquake event. Okay, so this is more a detailed explanation, okay, during the earthquake event, okay, which is from the fault or from the epicenter. Okay, so then when the seismic wave, which is the E naught, generated by the earthquake fault, reach the bottom of the foundation, okay, they divide into two types. Okay, so which is the E naught, which is the E1, okay, the wave entering into the building, and there will be the F naught, the wave being reflected back into the ground. Okay. So the E1 is called as the transmission wave, while the wave F naught is called the reflection wave. Okay. So this will be back to the what we call to the ground, to the soil, while this will be enter to the building from the foundation. Okay. So the transmission wave E1 entering into the building travel towards the to the top of the building with subjecting the building to vibrations. Okay, and then they reflect at the top and travel back down to the foundation. Here, a crucial phenomenon occurs for consideration of the SSI. Okay. So they migrate to the top and then going back, okay, again, okay. So they call as a F1, okay, and also there will be a R1 radiation wave, okay, when it reach the foundations, okay. So then there will be two they will separate into two wave, okay, which is the F2 and also the R1. Okay, when the wave that are reflect at the top of the building and traveling downward F1 reach the foundations, a part of them is transmitted into the ground while the rest is reflect back again and one start to move upward through the building. Okay, the former wave escaping into the ground are called radiation wave, which is the R1. Okay. The one that move up, they call as the F2. Okay. So when the amount of this radiation wave are small, the seismic wave one transmitted into the building and the building continue to vibrate for a long time. Okay, so it has like a cycle. So until the vibration is eliminated or completed. Okay, the apparent vibration condition become the same of the small damping of the building. Okay, so for example, if we have a very good damping system, okay, so this F2 or F1 could be minimized later on. Okay, the damping caused by escape of the seismic wave which has been transmitted into the building back into the ground is called radiation damping. Okay. So when the building foundation is forced to vibrate vertically, a stress called contact earth pressure is caused at the boundary between the bottom surface of the foundation and the ground. Okay, the distribution of this contact earth pressure over the bottom surface of the foundation is called the contact earth pressure distributions. Okay, so this is the common type of distributions of the foundation, where we have a rigid foundation rigidity type, okay, uniform soil classification type, and also parabolic distribution, also non-linearity are observed. Okay, so it depends on the loads and also the type of the foundations. Okay, so this is the common type of the foundations. We call it as a contact earth pressure diagram. Okay, so foundation and subsurface solution with an increased complexity, more involved method of calculating the force within the and displacement of the structure element are required. Okay. The use of the more basic approach that rely heavily on hand calculation or rule of thumb may not be appropriate in such situations, as there may be too many degrees of indeterminacy within the problems, or they may simple be too time consumed to use. Okay. Later on, the use of the finite element model allow the user to create soil structure model of the whole or part of the problem with relative ease. Okay. So similar like when we learn on the slip surface, okay, of the slope stability, okay, then we normally use the method of slices. Okay, so we can easily calculate by using the hand calculation. Okay, if we want to determine the factor of safety for the first time. Okay, okay, but this factor safety, it is not the optimum value. Okay, so as a suggestion, okay, most of the reference book suggest to use the commercial software. Okay, for example, we may use Studio, okay, to ease our work to determine the stability of the slope. Okay, so I need to plug in my socket for the power supply. Okay, this model can generally then be modified to respond to change in design or undertake parametric study that might otherwise take a great deal of time. Soil structure model can also provide us with the means of predicting the impact of one structure on another. Displacement and stress change can be calculated for different construction phases. Okay. So there is a little bit detail on the SSI approach. Okay. However, I'm not have any experience, okay, in using this SSI, because most of our design, okay, is related to a static load. Okay, so unless we have some important structure that we need to design, okay, by include the vibration effect, okay, in the design itself. Okay, so now we move to wave propagations in soil. Okay. This is to gain, okay, what we call as the shear modulus, okay, where we can use some of the instrument, okay, to determine what we call as the type of the wave. Okay, so in here, okay, there will be three type of wave are readily encountered and are of importance. Okay, so we have three. We have P wave, S wave, and the last one is the Relic wave. Okay? So the first two are terms body wave, which are propagated within the soil and comprise the compressional wave and the shear wave, the S wave. Okay? So in relatively soft saturated near surface sediment, which is likely to be a case for a large number of geotechnical problems, okay, the P wave or the VP is dominated by the bulk modulus of the pore field, okay, where the water is filled, okay, inside the pore, okay, or the water is hard compared to the soil, and the resultant VP may be close to that of the pore field. Okay. So if we are having a problems, we have a dealing with a saturated soil, okay. So it is wise to use or to determine the P wave value. So if the soil is unsaturated, VP can range from that of the soil metric with no pore field to that for the saturated case. Okay, there will be two type of condition. Okay, either it is without no pore field, or it only have a pore filled by the air. Okay, to that for the saturated cases. Okay. Therefore, the use of the VP to determine the properties of the soil is problematic. Okay. So, in that case, okay, the suggestion to use the S wave will be wise, okay, because the pore field do not carry shear stress, okay, so that the S wave is only influenced by the soil and not by the pore field. Okay. So because water cannot experience any shear stress, okay, it only can experience a compression stress. Okay. It can also be shown that during most dynamic loading event, it is cyclic change in shear stresses that influence the behavior of the soil. Okay, from the theory of propagating wave, it can be shown that the wave velocity through the soil is related to the stiffness of the soil by using the G equal to rho S square. Okay. So by using this S wave, okay, we can predict what will be the G or shear modulus of the soil, okay, by multiplying it with the rho or the soil density. Okay. Therefore, changes in Vs within the soil can be measured to determine the small strain stiffness, and the measurement of the SV is commonly employed to determine the dynamic behavior of soil at small strain. Okay. So either we can use the resistivity or the seismic, okay, to determine the P or the S wave. Okay, so this an example of the P wave in terms of the diagrams. Okay. So, and the B is show the S wave type, okay, in the diagrams. Okay. So shear wave, a wave in which the disturbance is an elastic deformation perpendicular to the direction of the motions, or also called as transverse wave. And compression wave, a wave with the disturbance is compressions of the medium. Compression wave also known as longitudinal waves. Okay. So the third wave, that is the frequency counted in the soil, is the relic wave, which travel along the ground surface. So relic wave measurement have gained in importance in recent years, since ground surface measurement can be readily and easily undertaken without the need for any intrusive investigations. Okay? So the author mentioned here that they can easily get the value for the relic wave, okay, because it travel along the ground surface. Okay, compared to the S and P wave, okay, so need to use equipment, okay, that would penetrate inside the soil body. Okay. So there is no direct link between the velocity of relic wave and the soil stiffness. Okay. However, it's been shown that for a nearly all value of Poisson ratio, so the R wave or the relic wave have a correlation with the S wave, okay, due to the Poisson ratio properties. Okay. So therefore, okay, by the correlation between the relic wave and the S wave from the Poisson ratio relation, so the Vs, okay, approximately equal to 1.09 PR. Okay, therefore, measurement of the relic wave can give a good determination of shear wave velocity, okay, from which G can be derived. So once we determine the VR, multiply with 1.09, so then we can get the value of the Vs, and this Vs will be used to determine the G. Okay. So this is an example of the relic wave as shown in a diagram. Okay, so that is some brief explanations, okay, on the wave propagation in the soil. Okay, we have three types of wave. Okay. So now we move to another topic, okay, which is discussed on the method, okay, to improve or to stabilize the ground, okay, in order to minimize the effect from the earthquake. Okay. So in both seismically active and inactive area, soil improvement techniques are commonly used as a site where the existing soil conditions are expected to lead to unsatisfactory performance. Okay. So unsatisfactory performance can be take many forms, but usually involve unacceptably large soil movement. Okay, the movement include horizontal or vertical or both components, and may take place during and or after earthquake shaking. Okay, in the absence of the earthquake shaking, unacceptable movement usually result from insufficient soil strength or stiffness. Okay. Okay. Consequently, most soil improvement were developed to increase the strength and stiffness of the soil deposit. Okay, so that is the idea of the ground or soil improvement. So during the earthquake event, the build-up of excess pore water pressure can lead to very large deformations. Okay, so this is due to the soil is very weak, or the density of the soil is very low. Okay, so it can easily build up for the excess pore water pressure. The most common soil improvement technique can be divided into 4 major categories, okay, where we have a densification techniques, reinforcement technique, grouting and easing techniques, and the last one is the drainage technique. Okay. So we have 4 types of ground improvement methods. So for the first one, the particle that we call as a densification technique, the particle that comprise a particular soil can be arranged in many different ways. Okay. The strength and the stiffness of the soil is higher, then the particles are packed in a dense configuration than when they pack loosely. Okay, so that is a common sense there. Okay? Where the strength and stiffness is higher, okay, due to the soil is compacted dense compared to the soil which is packed loosely. Okay. Also, the tendency to generate positive excess pore water pressure due to cyclic loading is lower when the soil is dense than when it is loose. Okay. As a result, densification is one of the most effective and commonly used means of improving soil characteristics for mitigations of seismic hazard. Okay. So due to that, densification is part of the common technique and also effective methods to be used. Okay. So the most common approach to densifications includes Vibro Techniques, dynamic compactions, blasting, and compaction grouting. Okay. So Vibro Techniques use probes that are vibrated to a soil deposit in a grid pattern to densify the soil over the entire thickness of the deposit. Okay. So I guess you are also very familiar with this type of methods. Okay. So this an example of the Vibro methods. Okay. Idea it can use in the small scale, or it can be used in a very large scale by using machines. By using large machines. Okay. So this machine can provide a vibration. Okay. At the end, it can pack the soil in dense conditions. Okay. So we have another method. They call it as a dynamic compaction. Okay. Where usually they use a steel plates, generally range from 6 to 30 tons, and drop height usually range from 10 to 30 meter. Okay. So it can be, it's very huge amount of energy, okay, released from this dynamic compactions. And the other one is the blasting. Okay, loose granular soil have been compacted by blasting. Blasting densification involves the detonation of multiple explosive charge vertically spaced 3 to 6 meter apart in drill borehole. Okay, the borehole are usually spaced between 5 to 15 meter apart and backfill prior detonation. Okay, so this is another method, okay, on the densification by using the blasting methods. Okay. So the objective is to dense the soil, okay, to reduce or to minimize the effect from the earthquake. Okay. The second method is compaction grouting. Soft soil, okay, this okay. So you can read later on. So they inject grouting material and then let it for a several period of time, okay, to make sure that it reach the hardened state of the material. Okay. Okay, reinforcement technique. Okay, this is by applying whatever stiff material, okay, inside the soil. Okay, either by using a piling system, concreting, or by using a timber. Okay, so this is example of the stone column methods, okay, where they inject or they install a column, install a stone, okay, inside the soil. Okay, for mitigation of seismic hazard, they are commonly used for improvement of recoverable soil deposits. Okay, so that is the use of the stone columns. Okay. So this is a compaction pile, okay, where they install a pile, okay, where it has some improve the seismic performance, okay, by 3 different mechanisms. Okay. So the flexural strength of the pile themselves provide resistance to soil movement. The vibration and displacement produced by their installation cause densifications. The installation process increased the lateral stress in the soil surrounding the pile. Okay. So then we have a grouting and mixing techniques. Okay. For example, for this case, okay, they are using what we call as grouting and also mixing. Okay, so this is what we call as a deep mixing method. Okay. So they mix a stabilization agent, either lime or cement, okay, with the surrounding soil.
Doctor, this one DSM, Doctor.
Betul. Deep soil mixing, deep mixing method, DMM.
Ground treatment.
Actually, when I did my PhD, I'm investigating on the performance of this deep mixing method by using a small scale physical test. Okay. So then the last one is the drainage technique. Okay. Eliminate by lowering the groundwater table prior to the earthquake shaking. So that is the idea of this drainage technique. So for example, the common type of drainage technique is the PVD, okay, prefabricated vertical drain. Okay. Accelerate the construction process of, it also can accelerate the construction process of the subsoil area. Okay. So the idea of all the ground improvement technique is to ensure that the soil is dense, okay, in order to avoid for the a high excess of pore water pressure during the earthquake event, which lead to a liquefaction effect on the soil. Okay. So that is all for the introduction part. Okay. So we should take a rest, okay, for 10 minutes before we continue for the second topic on the shallow foundation. Okay, so and it also easy for me to share the recording sessions. Okay, because it will take no, it will take a less storage. So I will stop first and then we take a rest for 10 minutes, and then we continue at 10:30.